Now I wanted to do an extended example involving a ramp with friction. These are probably the hardest sorts of problems that we'll run into multiple times in this course, so I think it's worth seeing definitely one complete example. So here's the problem. Let's say we have a block on a ramp. And the ramp has friction such that the kinetic coefficient is equal to the static coefficient, which equals 0.4. And the ramp is tilted at an angle of 20 degrees. Oh, and it's a 1 kilogram block. So the question is, part A, assuming the block starts at rest, what is its acceleration? I guess find A, period. So part B is do the same, except for an angle of 40 degrees. Okay, so I'm going to erase this. So write this down, pause it if you have to. And I'm going to erase this to make room for our picture. So we're going to start by drawing a picture. We have our ramp tilted at an angle of 20 degrees. We have our block on it, and it has some friction. I'm just going to remind us of that by putting a mu there. And we want to know its acceleration. Now, if it's going to accelerate, it would be in the sliding down the ramp direction, so I'm going to draw an arrow with an A and a question mark. All right, so let's get started. So hopefully by now you guys can just see what forces there are on this and write it down, but we'll do this one more time. So if we draw a little bubble around our object, there is only one thing touching the block, and that is the ramp. So the ramp could be exerting two different forces on it, right? We have normal force and we have friction, either static or kinetic. And of course, we also have one long-range force, and that is gravity. So these are our three forces, and we can draw them on a free body diagram. We'll draw that big over here. So we have gravity down, gravity straight down. Our normal force is perpendicular to the surface, so it is going to be up and to the right like that. And friction is parallel to the surface, which could be parallel up the ramp or parallel down the ramp. Well, like we said, if the block is accelerating, it would be in the down the ramp direction, which means our friction would be opposing that in the up the ramp direction. So if there is friction, it will be in a direction that looks like that. Okay, and that's our free body diagram. To improve on this, we could add one more thing, and that is put some angles showing the relationship between these different forces. Now, if this is our ramp and our block, our normal force is in this perpendicular direction, right? So the way I like to think about this is, if you imagine starting with a flat surface and tilting it up to an angle of 20 degrees, when you start with a flat surface, your normal force is like this, straight up. And so when you tilt it at an angle of 20 degrees, this also tilts at an angle of 20 degrees, which means our normal force is 20 degrees from the vertical direction. You can kind of prove this with more rigorous geometry, but this is hopefully a quick way of showing that makes sense. The reason this is useful is because what we really want, as you've seen in other videos, is this angle. And if this is the perpendicular direction and this is the parallel direction, so this is a line continuing through there, these opposite angles are the same. So this is 20 degrees. And if this is the parallel direction, then my parallel component is going to be in the same direction as that, which is going to look like this. And these are at a right angle to each other. So now I have drawn my triangle that has FG parallel and FG perpendicular, the two components that I'm going to need to find. So hopefully that makes sense. That won't be the last time you see this, but it also isn't the first time because we did it in the last video. So, all right. So now I know enough to find FG parallel and FG perpendicular, right? So our block was 1 kilogram. So our force of gravity is equal to mg, that's 1 kilogram, times 9.8 meters per second squared, which is 9.8 newtons. And that's the hypotenuse of our triangle. So FG perpendicular and FG parallel, we can just write down. FG perpendicular is adjacent to the 20 degrees, so it's going to be the hypotenuse times the cosine, 9.8 cosine 20, and that is equal to 9.21 newtons. FG parallel is opposite 20 degrees, so that's sine, and 9.8 times the sine of 20 degrees is equal to 3.35. And I'll put units on those. Okay, quick check. For a small angle like 20 degrees, do we expect this opposite side to be shorter or longer than this adjacent side? Well, I didn't draw this totally to scale, but I did draw this as a small-ish angle. And indeed, this is the shorter side of the two, so we would expect FG parallel to be smaller than FG perpendicular. So that's good. All right, so you basically always have to find those in the problem, so you don't have to think too far ahead to what you actually want. But we want to find the acceleration, right? And if we want this acceleration from forces, we're going to need to use Newton's second law. And the acceleration is in the parallel direction, so we want to use Newton's law in the parallel direction. So, we're going to end up with something like this. The sum of our parallel forces is equal to m a parallel. So we want to find what forces are in the parallel direction. Now, one of them, FG parallel, we already have. That's 3.35 newtons. The other one is friction, and that is what we need to think about next. So how big is this friction, and what does that mean in terms of our acceleration? Okay. I'm going to leave these up here and work below them because we will need those. Okay, so friction. So if our block is sliding down this ramp, our friction, Fk, is going to be equal to mu k times the normal force. So if our block is sliding down the ramp, we can plug in and get this number. If our block is sitting on the ramp not moving, then the static friction force is less than or equal to mu times the normal force. Again, this could be a different friction coefficient, but we're saying that these two are equal to each other in this particular problem. So depending on whether our block is moving or not, we might have to use one of these or the other. So in order to explore this more, because these are both the same value, we should calculate it and use that to think about what's going on. So mu times the normal force. Oh, right. We didn't find the normal force yet. I'm jumping one step ahead of myself. So to find this, we need to find what the normal force is. Okay, the normal force is here. It is in the perpendicular direction. And we talked about this before, but hopefully you remember. In the perpendicular direction, we only have two forces, right? We have the normal force up and to the right, and Fg perpendicular in the opposite direction. And we know that the normal force is as big as it needs to be to keep the acceleration equal to 0. So the sum of our forces is equal to MA perpendicular, I should say, and A perpendicular equals 0. So F normal minus Fg perpendicular equals 0. That means the normal force is equal to Fg perpendicular, as we saw in the previous video. So our normal force, we do know it is equal to this side, which is 9.21 newtons. Okay, now that we have that done, Now we can go back to friction. Okay, so mu times the normal force, that is equal to 0.4 times, 9.21. So plugging those in, we get 3.68 newtons. So 3.68 newtons is mu times the normal force. I'm not saying that is our force of friction. I'm just saying this value, if we calculate it, is equal to 3.68. So here's the question. Our block is starting motionless. We were told that it was not moving. And so if we plug in this value, so if we plug in the kinetic friction, that is, the friction force is equal to this, we get the following. We get the sum of our forces in the parallel direction is equal to Fg parallel, that is 3.35 newtons down the ramp, minus 3.68. Well, this is going to give me a net negative force, a net force up the ramp, right? So this minus this is minus 0.33. So that means if my block is to be moving on the surface, it is going to start accelerating up the ramp at a rate of minus 0.33. With a force of minus 0.33 newtons, and therefore with an acceleration of this divided by 1, which is also minus 0.33 meters per second squared. So we set the block on the ramp, we let it go, and it starts going up the ramp. Something about that doesn't seem right. So the kinetic friction doesn't quite make sense. Let's look at the static friction and see if that makes sense instead. So here, remember our static friction can be any value less than or equal to mu times the normal force. So it can be anything less than or equal to 3.68 newtons. And it's whatever it has to be to keep the block from moving. So can it be less than that and keep the block from moving? Yes, of course, because we have this 3.35 newtons down. I'm going to draw a little free body diagram over here. We have our 3.35 newtons down the ramp, and we have our static friction force up the ramp that can be anything less than 3.68 as long as it is keeping the block still, as long as it is keeping it from moving. So that just means our friction force is equal to 3.35 newtons, which is less than 3.68, yes, and those two are balanced. So our parallel acceleration is equal to 0. So just to formalize this, the sum of our parallel forces is Fg parallel minus the force of static friction, and that is equal to 3.35 minus 3.35, which is equal to 0. So our acceleration is equal to 0 for part A. Now we're ready for part B. Okay, these numbers are changing, so I'm going to erase these. So part B, remember, was this angle is changing to 40 degrees. And now that we've already done this once, the second part will be a lot quicker because I don't have to explain quite as much. Okay, this is staying the same. This is going to change. These are going to change. So these are now 40 degrees. And we have to figure out new values of Fg perpendicular and Fg parallel. So Fg perpendicular is equal to 9.8 times the cosine of 40, which is equal to 7.51 newtons, and Fg parallel is equal to 9.8 times the sine of 40 degrees, which is equal to 6.30 newtons. Okay, so these have changed. These are different values. So let's just right off the bat, can we have the same thing happen as last time? Can our static friction stop the block? Or keep the block stopped, I should say. So in this case, our static friction, remember, is less than or equal to mu times the normal force. We already know what's going on here. The normal force is equal to this. It's equal to 7.51. So mu times the normal force is equal to 0.4 times 7.51. That is equal to 3.00 newtons. So this is the maximum amount our static friction force could be, 3 newtons up the ramp, and Fg parallel is 6.3 newtons down the ramp. So can this friction be big enough to keep it from sliding? No, it cannot, right? Because, I mean, and we can show this, the sum of the parallel forces is going to be the 6.3 newtons down minus the maximum that this friction could be would be 3 newtons. And that is greater than 0, so we are going to accelerate. I should have erased this. A is not equal to 0. Okay, to figure out how big it is, we need to think about the kinetic friction. So we know we're going to slide, so we know we're going to have kinetic friction. In our kinetic friction, we don't have an inequality. It is just equal to mu times the normal force. And mu k, again, in this problem is the same as mu s. So we still have 0.4 times 7.51, so this is still 3.00 newtons. And that means that our force is equal to 6.3 newtons down minus 3 newtons up, which was the same thing we wrote before as a check on the static friction. So let's subtract those. 6.3 minus 3 is 3.30 newtons. So this is the net force in the down the ramp direction. Or if we were to draw, I can erase these now. If we were to draw a little free body diagram, we have 6.3 newtons down from gravity, the component of gravity pulling it down the ramp, right? And we have 3 newtons of kinetic friction up the ramp. So that's giving us a net force down the ramp of 3.30 newtons. Our acceleration is equal to our F over our mass. So that is our 3.30 over our mass, which is 1 kilogram. So our acceleration is equal to 3.30 divided by 1, which equals 3.30 meters per second squared. So our block will slide down the ramp at a rate of 3.3 meters per second squared. So depending on the angle of the ramp, it can be steep enough to overcome this friction and get it to slide, where, for a shallower angle, the force of friction pulling it down the ramp is not big enough to overcome friction. So yeah, this problem includes, both of those scenarios, which is why it's a good example. And we got practice finding the components. And so hopefully all the parts of this make sense. This is these ramps with friction problems are really good to be familiar with. One, because they kind of test a bunch of different parts of chapters 3 and 4 forces. And also they are pretty common. They show up and they may show up on a test. So it's good stuff to know.